Another property of organic molecules which is heavily influenced by the polarity is solubility. When we talked about melting points and boiling points as a function of polarity, we talked about association of a molecule of a given kind with the molecules of the same kind. When we talk about solubility, we really talk about association between two different kinds of molecules, one of which is the solute and the other one is the solvent. And all of you, I think, have heard about the rule like dissolves like. And in the next couple of examples, we're going to try to look at the illustrations of this rule and show how it really does have a significant scientific role. So the first system we're going to look at is solution of sodium chloride in water. Sodium chloride consists of sodium plus and Cl minus anions, which are organized in a crystal lattice, and they strongly attract each other. So therefore, dissolving them is going to be energetically unfavorable because this crystal lattice energy needs to be lost. However, when we expose sodium chloride to water, what we get is sodium plus anion, a cation, and a Cl minus anion, but they're not naked ions. They're surrounded by molecules of water. And sodium is surrounded by molecules of water which orient their oxygen atoms towards it, thus stabilizing its positive charge through the interaction with these oxygen-free electron pairs. On the other hand, chloride is surrounded by water molecules that position its hydrogen atoms towards it, thus establishing a series of hydrogen bonds which then stabilize the chloride anion. This process is known as solvation, and it's energetically favorable. And thus, the energy of solvation makes up for the lost energy of crystal lattice and makes the overall dissolution energetically favorable. Another factor that is important is entropy. If we think about crystal lattice, it's a very ordered system. And if you think about solution, it's a relatively disordered system because the ions are whizzing around at pretty much random orientation. And so we're going from an ordered crystal from disordered solution, which is good, right? It's entropically favorable. So this solution of sodium chloride in water is both entropically and energetically, so enthalpically favorable. But now if you think about dissolving sodium chloride in a nonpolar solvent such as hexane, things change. Even though entropically we will still go from an ordered crystal to disordered solution, enthalpically things are different because hexane, which is nonpolar, is unable to solvate either sodium plus or Cl minus anions. Thus, sodium chloride does not dissolve in hexane. Let's look now at what happens with nonpolar solutes. So if you look at a nonpolar compound, such as some long hydrocarbon chains, and try dissolving this in molecules such in water, what we're going to notice is that nonpolar compounds do not dissolve in water. The reason for that is both energy and entropy. Energetic parameter comes from the fact that water is within itself extensively hydrogen bonded. And if we introduce a nonpolar molecule into that solution that cannot replace those hydrogen bonds, it just disrupts those hydrogen bonds and we lose some energy of stabilization. So the energetic problem is that disruption is disruption of hydrogen bonds. Entropically, if we go from a very disordered network of water molecules where they're randomly bound to each other, and now introduce a molecule of some non-polar compound, then the water molecules will have to order itself around this non-polar solute. And so we're going from a disordered situation to an ordered situation, which is entropically unfavorable. So both parameters work against dissolving non-polar compounds in water. The final situation we're going to analyze is non-polar compounds dissolved in molecules like in solvents like hexane. And in this case, this simply put works, so we can dissolve non-polar compounds in hexane because both energy and entropy are working in our favor. In terms of energy, there are no hydrogen bonds to be disrupted. Molecules of hexane are only weakly associated with each other, and disrupting that weak association, or furthermore replacing it with the association between hexane and some non-polar compound, is energetically pretty much neutral. In addition, entropic factors work well for us as well, because there is no need for hexane to order around this thing, because again the network of hydrogen bonding is not existent in hexane, and furthermore we can now have this entropy of mixing, where we disperse a non-polar compound in a very large volume of hexane and thus make it relatively disordered. Finally, to illustrate one of these rules through a structural example, here is a molecule of ethanol, which has this hydrogen atom, which can bind to oxygen through hydrogen bonds. And this oxygen can come from either other molecule of ethanol or from a molecule of water, and this explains why ethanol is soluble in water. So we will finish this section on the intermolecular forces and their applications to both polarities and boiling point. And now in the next topic we'll look at the classes of organic compounds, which will serve as a prelude to our discussion, which will begin in the next lecture, of individual classes of organic compounds.